looking what round tables you want. I let the hotel room go through your district.
They got special funding.
Did they?
Yeah.
So we just do that one form and send it to him?
Yep.
Because they did that Excel, like you can get, this is what everybody is. You got a new registration form and then put it on that other one.
Yep, and then send it all.
I've been sending them most of my individuals so they can at least do name tags ahead of time and have that shit done.
I think I only got it.
We have 4 out of our office, 2 out of main, we don't have it.
It's just like,
all right, we'll get rolling again here for chapter 8, substructure and concrete quantities. So we've been talking a little bit about some parts of substructure. We've had some spread footing stuff, and we're going to concentrate a little bit more on this. A couple of the concepts like the type of abutments we've gone over a little bit. We will go back over them as well. Before we start, any questions as you mulling it over break about reinforcement? So what's the purpose of abutments? It's to retain earth and also transfers loads and forces to the footings and thus into the ground. As I have mentioned, there are certainly different types of loads that abutments will have to withstand. One is you got the load of the beams coming across, the deck, the beams, the vehicles, everything coming across to a bearing seat or a bridge seat, whatever we would term it, and then coming down the abutment into the ground. So that's a vertical load that comes through the abutment. We also have on the back side of the abutment, we have horizontal soil pressures that are pushing against the abutment, so it experiences those kind of loads. And so the abutment is transferring loads and forces into the footings and into the ground. The 3 most common types of abutments, and Andy talked a little bit about some of these. Nowadays, we're using a lot of these integral abutments. It's single line of pile, and the expansion joint is not at the abutments. The expansion joint gets pushed to the far end of the approach paths. And so that is really what these single line integral abutments are. Parapet abutments are what's been the bread and butter for years, and that's the ones where the beams will sit on a bearing, and it's all of that stuff's exposed to view. There's a little bridge seat and then a back wall. And typically the parapet abutments will have a joint that's at the abutment. Sometimes in the early interstate era, the joints would be kind of just beyond the end block, so kind of on the back side of the abutment. Now, most of the time, the joints will be on the front side of the abutment, a little bit easier to access and see what's going on if you have a leak and so forth. And the last one is semi-integral, and that's kind of a combination between the two. It does have 2 lines of pile, different than the integral abutments, and we will see that on some of these upcoming slides. The parapet abutments are designed to accommodate larger movements and then skews. So if we're, like our bridge here, we have a 30-something degree skew. And so when you have a skewed bridge situation, the movements can get to be a little bit strange. And so high skews are difficult to do with integral abutments. We also break up abutments into low abutments and high abutments. I'm not exactly sure why that designation, because it hasn't been something we've used a whole lot, but here is a depiction of that. There's still a couple of references in the spec book that talk about high abutments, low abutments. And so if this stem height, where the bearing is, or where the beam sits, the top of the footing, if that's less than 15 feet, it's called a low abutment. And it's a parapet abutment. There's going to be an end block up here with a joint. If it's a high abutment, it would be things that are greater than 15 feet in this location.
Looks like the end blocks are in different locations, the low versus the high.
Yeah, and this, I would almost say that that is not correct. I've never really seen that because, here's the reason. The approach panel sits on this little ledge that's right there.
Yeah.
And so this one, there's no ledge, so, you know, I guess they could show one with a built-out ledge, that, in the days gone by, that's how they were done, but that one doesn't show it, so I think it's just kind of sketched in. But yeah, good observation that there is that difference on that sketch. And then the single line, integral abutment would look something like that. So here's a parapet abutment. You can tell it's a parapet. There's no integral end diaphragm in there encapsulating the whole ends of the beams. This one, most likely, the footing is up in the fill there somewhere. Sometimes the footing will be way down at the roadway level, especially if they think in the future they may need to widen. But we have done some of these where the abutment was perched up in the fill like that. There's a slope paving coming down, and later the department says, well, we want to add another lane coming through this. Well, now all of a sudden you got to retain that slope, and so we've gone in and put soil nail walls. It's a kind of a top-down construction. You excavate like maybe 5 feet, put some soil anchors back in, put a shotcrete facing on there, and then go down 3 more feet and put in some anchors and shotcrete, and eventually then you end up with you know, maybe a 8 or 10 foot high wall right here, enabling you to get one more lane of traffic. So that's been done at times. So this is a parapet abutment. It says with curtain walls. So I more tend to say these are mask walls. The curtain wall is this little piece here that's kind of helping to hide the seat. Keep some of the elements out from the bearing area. The wing wall is, again, the part that's going back, or sometimes at a 45, or sometimes coming parallel to the roadway. Its purpose is to help retain the soil over there. The stem of the abutment is this portion here, from the top of the footing to the bridge seat. And then this is called different things. Sometimes bridge seat, sometimes bearing seat, sometimes pedestal. Different terminologies for the same thing. This portion of the abutment that's from the top of the seat up to the end block is called a parapet or a back wall. And see what else we have. Footing down there. So when we're forming the abutment wing walls, so there can be some little complicated forming. There's always going to be some kind of a chamfer, but here we're doing some forming to be able to construct that particular abutment. The plans will always have some kind of a grade line that where do you need the finished grade to go. And I think as we mentioned the other day, we always want at least 4.5 feet of cover from our grade line to the bottom of the footing. So that's just Minnesota frost will go down 4+ feet at times, and so that is what we have. So that's the grade line. And integral and semi-integral abutments, they're a little bit different, is that they accommodate the thermal movement at the roadway end of the approach panel. So you have the bridge, then you'll have a 20-foot approach panel, or sometimes more, depending if you have to square off. And that's where your joint would be. And it's not going to be necessarily a strip seal joint, it'll most likely be an E8 type of a joint. Mark will actually come back in on Friday and talk about that, but in the back, some of those rubber kind of square looking pieces, those are E8 joints, some type of a compressible seal that can be preformed, or you can have just a fold with some type of a hot core that goes in there as well. The amount of change in length of a bridge is dependent on, the big one is temperature, the change in temperature. The coefficient of thermal expansion is pretty similar for steel and for concrete. So for concrete it's 0.000006, if I have the right number of zeros, and for steel it's 0.65. So there's many 5 zeros and a 6.5. That means that they expand and contract relatively the same. But if we have things like fiberglass, it's going to expand at a different rate, and timber is going to expand at a different rate. But we do need to look then at what is the change of temperature and what is the length of them. The rule of thumb is for every 100 feet of bridge, the expansion, the thermal expansion is 1 1/8 inches. So that means 100-foot long bridge, and if you divide it in two, you're going to have a 1/2 inch at one abutment, 1/2 inch at another. If you got a 200-foot long bridge, you're going to have roughly 1 inch of movement at one end and 1 inch at the other. Or if we're offset because of the way we fix our piers, you might have a little bit more on one side than the other. So to talk then about integral abutments, it consists of a concrete abutment stem supported by a single line of piles. So, and those piles are going to flex. Andy talked about weak axis, strong axis. So we want it to be on the weak axis so that a substructure can move. And there's going to be a continual concrete diaphragm that is in there. So we'll have some pictures coming up that show it a little bit better instead of just words. The semi-integral abutment is different because it's going to have bearings that go under there, and then there's going to be multiple rows of piles, usually 2 rows. So that is the difference between semi-integral abutment and the integral abutment. There are some limitations. So the bridge design manual has these kind of guidelines that are in here. But integral abutments are really now the preferred option if we can accommodate them, because the joints are off the bridge and it eliminates the expansion technique. There's still the E8 joints, but they're a lot easier to replace. You can go ahead and quickly saw cut them, put the new material in, and you're done. As opposed to a strip seal joint, which again, we haven't even talked about joints, but they're the little expansion devices that get cast in, and then there's a rubber gland that goes between. So some of the criteria, integral abutments are used on bridges up to 300 feet long, skews less than 20 degrees. So you can see that's a lot of the bridge population that we're going to have in the state. 300 feet. That gets you across, highway intersections. It gets you over a lot of little streams. So a lot of abutments now are going to integral. It can be used on bridges less than 100 feet long, skews less than 45 degrees, so high skew would be something that works. If we have deeper beams, we can still use integral, but we would use the semi-integral type that works. A lot of times you'll see H piles used on integral abutments, but here's one with CIP pile. They're a little stiffer than weak access H pile, but it still functions and it still works. And so there we see the single line of pile coming up into a seat where then the beams will come kind of between these gaps in the rebar. So the thermal effects, how do these bridges move? So in a fully integral abutment, we see everything is tied together. There is some polystyrene kind of on the outside of this is a little bearing, just kind of a rubber pad. That's the only bond breaker, but otherwise it's solid concrete coming all the way through here. End of the beam, all the way, there's gonna be some dowels that will attach the approach panel, so there's no movement at this joint. Everything moves, and so as the bridge expands to the left, this integral abutment, these piles will essentially bend, and it will accommodate movement. And so that is how the integral abutment works. The semi-integral abutment, we have 2 lines of piles at least, a footing, and then a more conventional type of a stem. And then we see that there's this polystyrene. So the polystyrene is like that thick blue, dense blue foam. And so that gets put on there to help and to provide a way for movement. So it's 1 inch down there, and then on this vertical face, it's 3 inches. So that means it will squish as the whole bridge would contract, it would be able to squish that low density polystyrene. So it's also low density versus high density. That means it'll squish easier. And so that is how the surfaces where movement occurs in that situation. But again, we see an integral diaphragm. The approach panel comes in. We tie that together with some bars. So polystyrene is the thing to note there. And here's some pictures of some polystyrene that's put in there. That this would be able to compress as that as the movement tries to shrink. And so that, again, that makes it semi-integral because of that polystyrene. What type of abutment would this one be, as you can see it? There's semi. So there's a lot of bars that are tying back here. We really don't see any vertical faces with polystyrene that are in here. So that's going to be an integral abutment. Integral abutment, everything gets tied together. So here again, there's bars coming out of that bottom stem pour. We're ready to form around and get rebar all the way around for a diaphragm, all those kind of things. False work and form work are shown here, all of the ply form. Keyway down here. Somebody had a good point, might have been John, I can't remember, but the keyways, oftentimes the contractors want to shovel the keyways out. The specs say you have to do it per the plan. So the keyways in the plan are often a 2x6. So the intent would be you to have a good sharp keyway. But again, we see shoveling as the probably the preferred means, but like we talked, it also means that we're more liable to forget it if you don't have the board sitting right there. Okay, so again, we see, and actually something like this, I should back up the keyways on these integral abutments. There's quite a bit of force that's going on there. And so the keyway is important. It's not just, oh yeah, kind of nice to have. There's a lot of load that's getting transferred, including through that keyway. Construction joints, we talked about that when we looked at the plan review. And this is a picture of our bridge, the south abutment details. And we have a note in there, membrane waterproofing system will be needed here at any of these construction joints. So notes 1 and 2, membrane waterproofing, and then a construction joint with a 2x6 keyway in the parapet. So those are all things, so in this case, the 2x6 keyway is the joint in that vertical, so we're looking down at it, is where that keyway is. So construction joint, is a construction joint something that's optional or it's required? It's required. So what's it called if it's an optional one? It's permissible, exactly. So permissible joint is something the contractor can choose to use or not to use. So membrane waterproofing in these locations. And I know I have some pictures somewhere of membrane waterproofing, so we'll get to them in, if not this presentation, another one. So the permissible, so here is a picture then of the permissible joint. Often it's this joint here between the seat and the parapet, or the back wall. It's a permissible joint, it's optional, that they can use it or not use it. And there's a note there, note 4, again, is membrane waterproofing if the joint is used. So membrane waterproofing if the joint is used. And here, yeah, so here's some pictures of membrane waterproofing. This Melroll has been used for years, it's a good product. But we see here that they have covered up some areas that probably had some form ties in there, covering up any of these joints, covering up vertical joints. You know, if we had a vertical construction joint, it would also be vertical right there. So the intent here is to keep water. So again, the picture. This is the back of the abutment. This is going to get all filled up. There will be some water that will get there, and we're trying to eliminate water getting through the joint, the construction joint that's there. So, you know, thus they're using the membrane water. 371 near Fort Ripley. So just an example of an integral bridge. You look at this, and the first thing we can see is there is. I don't see that there is an expansion joint out here. Not exactly sure where the abutment is with this configuration, but I think it's right here. And we don't see an expansion joint, a strip seal expansion joint. The beams are cast into that abutment back wall, means it's an integral abutment. And so some more of the details. On our bridge, what type of abutment do we have on Bridge 2738? So here's the detail of our deck. And so what kind of things do we look for? So what do we have for the type of abutment on our bridge? Integral, semi-integral, parapet. Those are our options. Parapet. So what kind of things do we look for? Expansion joint is one thing. So look for expansion joint. How about lines of piling? There's two, so by that definition, it means it's not going to be what? Integral, because integral has single line. Still could be a semi-integral, depending on what other details we see. But it does have an expansion joint that we see right here. So that is going to point me to say that it's going to be, so there's sheet 20 and sheet 35, a couple places we can see it. So we see no integral diaphragm, so that, and actually I'll point out to maybe color this in, but this is the end diaphragm right here. You might say, well, that's integral, it's going right between the beams. Yes, it is, but it's not fully encompassing the beams, and it's not fully tied in then with that end block. So it's not integral diaphragm, even though that diaphragm is cast. It's like a thickened section with a little bit of a drop section here. Okay, we also see strip seal. We see two lines of tile, so it means it's a parapet abutment. So there are things we're looking at. Joint, a couple lines of pile. The joint is up here. Okay, so let's move on from abutments to piers. So piers can be made of different materials. Certainly timber could fit in here as well, but we're going to concentrate on concrete, steel combination of the two. So that would be the typical kind. Most of our piers are going to be reinforced concrete. Occasionally we do have steel piers that are used. The common type of piers are hammerhead, multi-column, and caissons. So we'll talk a little bit about each of these. So multi-column piers are very typical. And the common, especially for a roadway over a roadway, and that's going to mean there's a couple of concrete columns and there's a concrete pier cap. Or possibly it could be a steel column and steel pier caps. They're relatively easy to construct. They're widely used in the past. And when we use them to cross the railroad track or things like that, and also even within the roadway zone, we would put a concrete strut between the columns to provide additional support in case of a derailment or vehicular crash. MnDOT has really been concentrating lately on adding crash struts to roadway bridges. And even if you're doing some more minor work up on the deck, a lot of times they're requiring that we go and look at the crash strut and the crash wall. And do we need to add that as an add-on? The hammerhead piers are over on the upper left here. It's a pier stem, and then the pier cap cantilevers out from that. So there's several. I think I got a picture coming up of the bridge in St. Cloud, but very typical. And a lot of times these are utilized in water crossings. Pile bent piers. Very typical on smaller bridges. Remember, there's a little tighter tolerance for driving those. You keep them in a decent line, and there's a pier cap on the top. And the multi-column pier, basic pier, looks like that. Forming the pier columns. So here we see they have a big form. This is perhaps a column that is tapering as it goes up. And they put one big form behind there, and then they have some chamfer strips going up to define the limits, and then they'll attach the form obviously around each side as they go. The pier caps oftentimes will have a step like this. So in our plans, remember I made mention one time that those pedestals are pretty tall. And another way to do it, instead of making tall pedestals, is you just step the top of pier concrete, and then you might, instead of having a 12-inch pedestal, you'll have 2 inches to 4 inches. So this one has steps instead of just taller pedestals. This is one showing a pier with a hammerhead pier with some decorative details. And I'm not sure if this looks similar at least to the bridge in St. Cloud that's in the Wetterling Memorial Bridge. But I guess I'm not positive if this is it, but it has similar look to that one. So they're a pretty clean look. You just put a couple little insets in, and it cleans it up pretty well. A typical pier detail might look something like this, with a couple of columns, with a cap up on the top, and yeah, so that is how we can make them work. So the finished pier and abutment would look something like this, with a curtain or the mast wall. Over there shown on the left, we got all the bearing seats or the bridge seats. we've set the bearings on top of there, ready for the beam. So these guys are ready for the beams to come across. It looks like we might have different spacing because we have an extra bearing in here. So it might be a long span on one side or short on the other. Pile band, very typical. Sometimes they're using water like it's shown here. This does cause some potential for debris to catch in there. So if there's a lot of debris in a river, they might not go with this. Or sometimes we have done these driven piles, so a CIP pile bend, but then cast. It's not a full pure wall. You're not designing it for loads. You're more designing it to be something that will restrict the timbers from and the logs that are floating down from wedging themselves in. So what's that? To deflect logs, yeah. So instead of a log coming down here and it's coming and then all of a sudden it twists itself up and it gets behind there, and pretty soon you have a big old mess. And so yeah, it'll deflect the logs. And that I've seen several bridges that are constructed that way. Because it is a lot easier, if we did a conventional pier, like a hammerhead pier or a shell, a fixed pier shell, you'd have to dewater it. So you'd end up with a big cofferdam and constructing a footing in the dry and whatnot. It's pretty expensive. So this way, you can do this method. Then once your piles are driven, actually they can do kind of just a little, instead of a true cofferdam, they could maybe do some kind of just a set, some sheets, and it'd be cheaper than doing a pure cofferdam. This one is a lot of aesthetics on some abutments. So this is Beltrami County, pedestrian trail up there. Quite a bit of aesthetics that are going on here. Melissa will talk on Friday about the requirements for aesthetics. And there's some criteria, and it's they determine is it a class A, B, or C bridge, or 1, 2, and 3, I think. They'll pay up to like 7% if it's a real visible, highly visible area, or just a couple percent if it's a basic bridge. And some of these have some pretty unique things. And we see again the concrete colored, make it look like stone. It's pretty, but it does cost quite a bit of money. Went on a trip one time on a scanning trip to see how New York State did their bridges. We were looking at high performance concrete, and talking to one of the guys there, and he said, "Oh, our aesthetics are just out of this world." And what it was is they had the emblem of the state of New York right here, and I said, "Be thankful for what you have," because we were already. This is 25 years ago, probably. We were already way beyond that with aesthetics. So. But it does look nice, and keep them maintained, and keep the graffiti artists off of it. So this is the bridge just above the Rochelo Pit, Highway 153, in Virginia Evelyn area. A lot of beautiful aesthetics in really everywhere we go. And these, it's more a stain, just a little form liner, and then they stain them up. Okay, so what are some material requirements? So concrete and concrete material are subject to testing for 1603 and 1604. And part of that says you are required to review the schedule of materials control for the required tests and samples needed for project acceptance. Another printing, a little bit of snafu we had, usually we try to print just 3 or 4 copies of structural concrete, scheduled materials control for you guys. Something got missed in the translation. There's a whole bunch of full copies, 11 by 17. Scheduled materials control, if you want a copy, they're on the back table. But we will, for this example, we're just gonna look at what we would need. So a little question for you to get our minds away from just listening to me. So how many slump tests are needed for Bridge 27-138 south abutment, stem, and wing walls if everything is placed at one time? So we gotta find, we have one for every 100 yards, plus what? What about right out of the gate? First one. Okay, so now I gotta figure out, we're gonna do the south abutment, stem, and the wing wall. We're doing everything at one time. So we gotta find out what that quantity is and then figure out how many tests. So help me out. 1 per 100, yeah. So we need to know what kind of concrete, so what kind of concrete are we going to be using for the abutment, stem, and wing walls? Stem and wing walls. Okay, anybody find what type of concrete do we have for stem and wing walls? 3B52, very good. So we have 3B52.
280 yards,
280 yards, where do you find that?
page 20.
Page 20. So there's a little summary of quantity chart in the upper right, the north and south abutment. And so you look for structural concrete, 3B52. So it's the second line down, and it says 280 under south abutment. The column for south abutment is 280. Okay, so that's some of the parameters you need. So how many tests are you gonna have to take? 3. Huh? 10. Why 10?
Because there's construction joints.
Very good, except my question said,
Well, you could, when we slope it,
if everything's placed at one time.
if everything's placed in one time.
But you are, that was very good. I think you might be the first person that's come up with that in the, I don't know how many years we've had this little question on here, but that's very observant that yes, we can't place it all at one time.
And that's assuming they use the joint to the parapet too,
Yeah,
and you do it all separate.
yeah. So you could have, if you have multiple pours. I mean, the way the plan is set up, we're gonna have at least 4 pours and probably more. Because of the need to put the construction joints in. Although what they could do, and oftentimes they may form everything, and they may, if it's 4 pours, say pour 1, 2, 3, and 4, today they might do pour 1 and 3, leave that gap in between, and then 72 hours later do pours 2 and 4.
That would definitely.
Okay, so if we do everything at one time, 280 yards, how many slump tests? 3. So how do we find that? So we find that, so slump, 1 per 100 yard plus test the first load each day per minute. First load plus 1 per 100. So we find the type of concrete, and it's 3B, so it's this grade designation. So yes, this particular chart applies here. Grade B, S, X, whatever. Find how many cubic yards. And so on the next slide, we would have from page 20, you guys have all found this, of concrete. Is there the 3B52? And then how many cubic yards of concrete? So it's the 280. where slope test required would be 1, so the first one plus then 280 minus 100 over divided by 100 would be 3. So you would have, for the way that question was, you would have 3. Again, in reality, it's probably going to be a different number because we're going to have multiple 4s. All right, how about rebar placement and substructure? So Mark brought us through rebar. Rebar that is in concrete that is not exposed to air will typically be non-coated or black reinforcement bars. So on this sketch, which is what bar designations are only in the footing? Or bar numbers, I should say, are only in the footing for the south of that. Maybe there's too many. Tell me what's the starting number and what is the ending number in our table. South of bottom. There are going to be bars that are only in the footings. Did we find what page we got to be on? So there'll be multiple ways we can find this. We can look in the details, we can also look in the bar chart. South abutment reinforcement. What's the first bar? Let me say it this way. What's the first bar in our bill of reinforcement for the south abutment? That's an abutment. I mean a footing bar. B601. So you see, there's no E at the end. So that means it's an uncoated or black rebar. And then there's a whole pile of what's all the way down through what bar is the last bar that is not epoxy coated. B524. There's a whole mess of bars, 01 through 24, with a couple that looks like they weren't in there, but roughly 24, 22 bars. Different bar designations are uncoated bars. How about this bar here, the B926E? It's in the footing down here, and then it comes up into the stem. Is that going to be epoxy coated or not? Epoxy coated. So we would know that because we've learned that if it's not completely in the footing, it's epoxy coated. Plus, of course, we see from the bar designation, 926E, the E means it's epoxy coated. So those are things. So rebar that's partially or completely in concrete exposed there will be epoxy coated. So that's these doubles. What is the rebar designation for the transverse bars in the top mat of the south abutment footing? So this is a kind of terminology. So sheet 14 of the plans. Transverse means we're going in the short dimension for this question. So we look at a section that looks like this. Transverse would mean we're going this way. Longitudinal would be going in and out of the page. So the question is, what's the rebar designation for the transverse bars in the top mat? So this is 505 through B511. Everybody see that? So it's this bar that's right here. That's coming across. Those are the transverse bars. And so we see that it's B505 through B511. What do we see different between the B505 bar and the 6, 7, 8, 9, 10, and 11? What kind of things are different? Is it a different diameter of bar? Is it a different epoxy coating? Is it a different length? Length. See, so in our bill of reinforcement, bar numbers on the left and the number of bars and then the length. And so we are from here able to see that, okay, there's some little tiny bars here. The last one is only 3 feet long. Almost to the point why I even bother putting a bar in that's only 3 feet long. There'd be another way to do that, and that's called a series. And we're gonna, we'll be coming up here pretty soon, I think. So, okay, so B505 through B511. So I'm not gonna do series until we get to right here. There it is. Series bars, they're rebar that vary by a constant increment for each bar. Oftentimes they're used on wing walls. So a wing wall starts at 20 foot high right at the abutment. It tapers up to maybe 6 feet high at the end of that wing wall. Rather than detailing every bar to say, okay, this bar is 17 foot 6 inches, this bar is 17 foot 2 inches, this bar is 16 foot 10, whatever. We're going to just say we have 10 bars and they go from 15 foot 0 to 12 foot 0 and that equal spaces. So we'll look at an example. Okay, so on page 14, looking on page 14, there are some bars over here on the left. So the B554E, the B555E, and then there's other ones, but let's just look at those. It says in the second column, or second and third together, it says 1 SCR, and that means series, of 5. This I'm on 554E. 6 foot 1 inches to 7 foot 5 inches. And so we then know that there's something is varying in that bar. Well, just by that length, we don't know exactly because that bar, the little bar detail shows it's like a U-shaped bar. So we need to find out from our U-shaped bar, and so we look right here at what kind of thing is varying. And the way these tables work is it might be easier to go to the top one. So this B569E bar is the top one. It has a 6-inch dimension right here, and then this is like a dimension line almost. And then this leg dimension is whatever that is of 1 foot 6. And that also means both of these legs would be 1 foot 6. Okay, so now to take our number, our 554E bar, it says it's a series, and then this number is varying. It's 2 foot 4, 2 foot 1 to 3 foot 5. Oh, it's just I can't read, that's why. 2 foot 1. 554, that's, okay. 554 is this one. That's what I can't read. Okay, 2 foot 1 to 3 foot 5. So that means that dimension, the first bar in the series is 2 foot 1, that dimension. The last bar in that series is 3 foot 5. Each one has the same leg distance if we take this down and whatever that one is. That leg is the same. And then we would, then each bar, the rebar manufacturer, if it says one series of 5. So there's 5 bars. We know that the longest one and the shortest one, and they have to figure out then what is the dimension of each one in between. Okay, so let's look now. I'm gonna have a little question for finding where these things are. So 555E bar, we looked at the 554. 55E is a pedestal tie. And so here is the 555E, 2.4 to 2.8. Oh, and I was going to say, who can tell me where these are? What page can we find? I mean, we can see them. But who can tell me what page can you find where the spacing of the 555E bar is? What I hear, 10? Okay, sheet 10. Everybody able to turn to sheet 10 and locate where it's going to dimension where the 555E bars are. What's the spacing of those things? Right here. 3 foot 4 inches. Is that the spacing between the bars? Okay, it says 5 equal spaces equals 3 foot 4. 6 bars. Is the spacing between each bar 3 foot 4? No. The total will be 3 foot 4. But there's 5 spaces, so each one is going to be whatever. We'd have to do the math. 8 inches or something. Is it a constant dimension across that whole pedestal?
No.
What about on the other side of the light? That's right. 6.5. So it's 1 foot 11. There's 5 spaces in there. So yeah, I mean, we're gonna do the math. So what that means, and so the little diagram here, this shows the on sheet 10, the B555E is space. 5 equal spaces equals 3 foot 4. So again, we can do the math, and it's around 8 inches. On this side of life, it's 1 foot 11. So at the edge of the bridge, because our bridge is skewed, we run out of room for that pedestal. And so that little pedestal is not a square, but it's some kind of a trapezoid. And so on the one side of life, we're spaced, 5 equal spaces, and it says flare is shown. 2-inch minimum clearance between the reinforcement bars. So you never go less than 2 inches, but if we do 1 foot 11, that's say 24 inches, 23 inches, divided by 5 would be nearly 5 inches, 4.5 inches. That makes sense? Anybody lost? Substructure rebar for columns, pier caps often are tied on the ground and lifted into place. This is a picture from 35W over Minnesota River. And you see it gets to be pretty nasty. It's something we want to stay out from under for sure. But obviously they need to get that thing into these forms. So you want to make sure that the forms are built so that they have cover once this thing gets put down in there. they'd have the correct cover. So those are all things we can be working ahead of time to make sure that we do have adequate cover. There have to be a lot of strong backs, a lot of things like that the contractor is working to make sure that everything stays tight. Obviously, you start lifting this up and things start moving all around, it's going to have a hard time fitting into that form. Concrete quantities are something that you as inspectors will be doing for partial payments, for final payments, all that kind of stuff. So concrete is typically measured by volume based on dimensions shown in the plans. Oftentimes, our concrete things will be a P quantity, meaning you don't have to do detailed calculations, but we need to do enough to make sure we're at least in the ballpark. Each mix of concrete will be measured separately, no reductions made in the concrete due to metal reinforcement, steel pile heads, things less than 2 inches in that dimension. That just means we don't have to get down to the nitty gritty and say, oh, you have a number 8 rebar in there with a 1 inch diameter, and I'm going to deduct off all that because in total it'll come up to 1.5 cubic yards. No, it's all the outside of the wall. So you as inspectors should always familiarize yourself with the plans, with the things that we have the details. It's useful to coordinate your concrete testing. Like we said, it'd be 3 slump tests if we are doing everything at once. But if we're doing multiple pours, well, then it's probably only going to be 1 a day. Type deal. The differences in computed and as delivered are easier to resolve if we've done some quantities ahead of time. What if you find something that appears to be a plan error? It'd be a good time to ask the designer. What do you get? How do you get 1,000 when I'm coming up with 750? When we have different pours like we would have here, where we have construction joints are required, and then if you have something with all of a sudden you run out of concrete, the truck comes and they're done. It's a good check then to have an estimate for the quantities and to see did something else go wrong. Okay, we're going to just do a little math exercise here. So the class exercise is compute the concrete volume for Pier 1 footings. So all of the footings, what's the concrete volume? So you got to find the dimensions and calculate the volume. So again, if you look at it in your presentation, it gives you the answer, but see what you can come up with. Anybody struggling to find the page where we can find the information on the dimensions? Okay, who's got a number?
128.
120, we got 120 in cubic yard, or 128? 128 in cubic yards?
128.
Yes, I heard that. 128, see some nods. 128. Anybody else get something else? In case 128 isn't right. Okay, let's see what we have. Okay, so you found that it's 12 by 12 and the thickness, so 12 by 12 in area. So plan elevation 4 feet. So 12 by 12 by 4, simple math. Again, there's multiple ways we can do it. We can take cubic feet and then divide it. I mean, literally, you could put this into yards, divide each one by 3, and then do it. This one shows 576 cubic feet per. Divided by 27 is 21 cubic yards each. There's a total of 6 of them, so 128. So that is good. Everybody get that? Pretty basic math. Next one is compute the concrete volume for pier columns on Pier 1. So there's 6 of them that are typical. Give you some elevations here, but you can look at the plan. So you got to remember what's the formula, how do you get volume of a column, of a circular column. Anybody remember that one? Okay, so let's see if we can crank this one out. Okay, anybody starting to get an answer yet? Still crunching. Get a more complicated formula. Okay, anybody get a number yet? What do we got? 37.6. Is that per column or for 6? For 6 in cubic yards? 37.6, you guys agree? 37.6. Okay, let's see if that's right. Okay, so how do you find the volume of a cylinder? Pi r squared gets you what? Gets you the area times the length. Pi r squared times the length. Or if you've learned it differently, it's pi d squared over 4 is the same as pi r squared. Just two different ways to do it, depending how you learn that formula. So the volume is pi r squared times the height. And we just put it so we can see it a little bit bigger. Volume, pi r squared times the height of the cap. We can do it by elevation. I think there's somewhere in the plans that actually give us the dimension as well. So then just do the math. It's 169.3 cubic feet per column. 6 columns, you get that much, divided by 27, 37.6-ish cubic yards. So that's what we have for now. And any questions on how to get the volume? Okay, there's other ones here. They're probably in your presentations if you follow. I'm not going to go through this, but same thing would hold. We can do like the pier caps. We can do them differently. You can take like each little step here and add it up, or you can take one big one like that and subtract it. So different ways you can do it. This kind of shows how you might do it. You might break it up vertically, like on the bottom there. So end of the day, you should come up with the same number. So a couple more things then on quantities. If there's unexplained discrepancies between field quantities and the plan estimate, engineer will transmit a copy of the plan estimate columns to the project engineer. So that's just saying, if you can't reconcile that, just ask the engineer, the design engineer, what kind of things did you have? And then as far as the peak quantities, per that spec 1901, for peak quantities, unless there's a discrepancy or there was a change in the plans, we would pay based on that. It's important for the inspector and contractor to review the site in advance of the pour. There's a lot of things we want to do. There's guidelines in the bridge construction manual that talk about concrete placement. Among the things that the spec book has is do not drop concrete more than 4 feet. So on a bridge deck, we're pumping a lot of things. Sometimes they'll come in a bucket that the concrete truck will dump in a bucket. The bucket gets put up and you dump it, but we want to minimize the distance that concrete is dropped. Why? Anybody know? Anyone want to venture a guess? Segregation. So it's segregation that is the problem. We also want to use lifts 1 foot thick max. There's actually things in the spec that say you can increase that if needed in some situations. But we also want to, so we put a lift on there, and we want to come with the next lift within an hour. Otherwise, that first lift will start to harden up. But we always want to vibrate, so you get the lift in there, and then say 30 minutes later you come back. You want to vibrate so that we are going down into the previous layer as well. So in 2401 3C, there's additional things that can happen there. What kind of things could be problematic here? Water. So we want to make sure that we can inspect everything is set. We also want to cast in the dry. So it's hard to tell if there's water down in here, but certainly there's some risk of water just seeing how the water is on the site. Curing. So what are the requirements of curing? 2401.3.G is the main go-to for curing. And it includes a table of 2401.3-2, which we had looked at previously. I said we're going to get used to this table. And this is on spec book, page 372. So again, just be familiar with how where these tables are. There's three main curing tables, and we'll be talking about all of them. Some apply only to that. But typically for substructure, which we are learning about right now in this session, it's typically 72 hours for substructure. And so if we look at that table 2413-2 on page 372, we can look down there. It's the substructures here would be pier caps are 72 hours. Sections not including in superstructure is 72 hours. So that's the third from the bottom. So that's kind of a catch-all for the minimum curing period. We also, though, need to be aware of the load limits that can be applied to the substructure before minimum curing time has been reached. And so, for instance, actually that's for pulling the forms. Yeah, there's nothing really for substructure. Actually, let's see. Okay, so let's look to the third to the bottom line, the sections not included in superstructures. Unless otherwise specified, it says minimum curing period is 72 hours, and then we go over minimum strength to pull forms. It's 2,000 with the, like a not equal to sign. And that down in the bottom says engineer will require verification of the minimum strength when air temps drop below 40. So always be looking at the notes and the things that we do. As far as minimum strength, we can use maturity or field cylinders. So the spec book allows both. There's been a bigger push recently for the maturity method. And I think when Jacob Gave comes in next week, and he's in on Monday, he'll talk perhaps a little bit more about that, the maturity method. But essentially it helps us control what the strength is. And so there's just the spec here about maturity method, that engineer will allow maturity method. So this is kind of a change in the spec in the fairly recent past. So table 2401.3-3, so that is on page 373. It's acceptable curing methods. And as we're looking at curing things like footings, like abutments, whatever, there's different things that might work. And so that table shows what's acceptable for footings, for pier caps, for pier columns. And then the columns going across, there's different things that are acceptable. So there's membrane curing, AMS and type 1D. So we can look at, those. There's curing blankets, there's wet curing, there's form cure, and SSF type 2. So we'll be talking perhaps a little bit more about some of those. But wet curing is always an option. Contractors don't always want to do wet curing because it takes some effort. So perhaps sometimes they just leave the forms on, and so form cure might be what they prefer, unless they need to reuse the forms on the next section. There's been a lot more emphasis on mass concrete, and for this one, we actually got to turn to our special provisions. So it's one of the little packets that was handed out. And I'm just going to get mine, so I have it here. If I can find it. So under concrete bridge construction, this is actually a fairly long section. good either. They printed for the 2023 class, so.
So it's online when it's 2023 class.
Is it?
Yes.
Okay. I'll have to get them to update that. Sorry about that. We had different people doing stuff this year and it has not worked out the best, so. I'll talk through what the mass concrete things are, because it's going to be correct here. So what I think is our special provisions, which should have been printed, this is what we have. So for mass concrete is for elements that are bigger than either 42 or 60, 48 or 60 inches. Concrete, as it cures, generates heat of hydration. It can get very hot. The 35W video talked about that how concrete literally can heat itself up internally from the internal heat of the reaction of all of the cement and the positive and stuff. And so we want to control that temperature. And through time, we have learned that if you're less than 48 inches, the heat can dissipate. If you start getting more than 48 inches, it gets to be harder and harder for especially that center portion of the heat that's generating to get outside. And so that's the reason for these specs. And it's included in the special provisions for anything greater than 48 inches or 60 inches for footings. If thermal heat gets too hot, and the differential can get between hot and cold on the surface, you can develop cracks. So that's the reason for this. We also want the max temperature to always be below 160. There's something that's called DEF, deferred intricate formation, delayed intricate formation. And if we say under 160, we don't see that. So we require on mass concrete for the contractor to instrument. And they'll use little things. Actually, I have one sample here, and I'll go get it. But there'll be little readers that are almost like little film canisters. That they put into the concrete, and the newer ones are probably not this big. There's some smaller ones, but essentially they put this into the concrete, like down in the middle of the pour. They connect the wires to, actually sometimes they just stick out and they come in with a reader and check the temp. But anyway, it'd be little things that look something like this that can check the temperature on the inside and near the outside. And so we want to then, within the first 48 hours, the temperature differential is 45. As it starts to gain strength, we say you can get a little bit higher differential. So that's what we need. Also in the plans, if we have the recent plans, they would show a little M for mass concrete. So when we get those, we will also.
So what do they do if the temperature differential gets too high?
There's nothing we really can do. It almost goes outside of what we would think would be working, but they will actually insulate and keep the heat from going, and that'll
Keep the temperature
more even. But if it starts going, if that internal temperature goes up, it's hard to control it. So they have over time been good at modeling, what the anticipated temperatures are. But on the Wakota Bridge, I still remember the engineer who was doing the thermal model, and it's some of the first ones we did. And he was sweating bullets, because as he was tracking the temperature and it was getting up against the limits. We had different limits back then. But I don't know if he slept there for a couple of days, because the temperature differentials were troubling him. And it stayed like right at the peak. There was a point where it was pretty close. So what are the options? They look at the concrete mix. They add fly ash, ground granulated blast furnace slag, silica fume or ternary means all three of those combined together. 35W video showed cooling tubes, they use cooling tubes. Or heating blankets or insulated forms. They literally keep everything a little bit more uniform. So those are things that they can do. Substructures are the elements that are most likely to be cast in cold weather, and they then require cold weather protection. Contractor has to have a cold weather plan and maintain temps between 60 and 120. Premature loading, not as likely to occur in a superstructure because it's hard to put major loads on there, but we need to be aware of that. But substructures, sometimes they can sometimes happen before the minimum curing time is reached. There are, over time, there used to be a lot of heated discussions between contractors and inspectors, engineers, over when can we start going up. We've cast this footing, we've cured it for 2 days, and we want to start tying rebar for the pier column. And some inspectors would say, no, you need 72 hours, and others would say, okay, you can disturb it. So we added a spec a number of years ago to say, so long as you provide, you're not going to freeze it or excessively dry, you can go along and you can start to tie for your walls or your columns or add forms and so on. But end of the day, when they go home, they have to put the curing back on. The surface of concrete structures have to receive ordinary surface finish. So that's in 2401. It describes what that means, and we'll just talk about some of them. So page 355 of our spec book talks about ordinary. All concrete surfaces have ordinary. So it's things like, I don't have that thing, but the little cone I showed, you know, they break off, you'd have to put ordinary surface finish on that to put it up. So you examine the surface, look for unsound or defective areas. If there's excessive porosity, honeycomb, they need to be removed and replaced. And we need to remove any fins that are like between form surfaces, any irregular projections, surface cavities larger than 3/8 need to be filled. And so it shows here clean, saturated water filled with mortar, and the mortar is given right here. So these are all parts of the spec that are in that portion, but they need to do that. So that's page 356 of our spec. There are some areas where we would allow them to use silicone caulk, and if it's areas that it doesn't affect the appearance. So that's something that could be used, and there's an APL for that material. Sack rub, sometimes they just do literally a sack rub of that material over the whole surface, and that will enable them to fill in all those voids instead of using just ordinary on the spot here, spot there. And so the sack rub oftentimes might be easier for them. And so I just mentioned about the form tie holes, that has to be done under ordinary. And then there's other specs there that a special surface finish. So you always have ordinary. A special surface finish is like adding a coating to the concrete. And that's only as required in the special provision. So it's going to be defined. It's going to say, okay, you need to do all front faces of abutments. You need to do all edges of deck, whatever. You're going to have something, edge girders, whatever. Use a department-approved product. And per our spec now, the SSF, or special surface finish, will be SSSF type 2. You're going to hear this a couple different times. SSF type 2 is a single component. It comes in a bucket, they mix it up, and they apply it. by spraying. Even though this says type 2, it's a one component product. It is the go-to now. It also functions as a curing agent. When we get to barriers, we'll see that this product can be used at a low, actually we might have a, yeah, it's right here. Surfaces to receive it shall be power washed with clean water, but if we use SSF2, it can be applied within the 24 hours. Which is right there. It can be applied without flushing on concrete less than 24 hours. So this is, the reason we started doing it actually is due to barriers. At the last thing cast, it's November, it's too cold to apply stuff. Well, if we had to wait 28 days. Contractor has to submit a quality control plan for this. So the specs have a lot of different things on quality, and there is obviously we don't want rungs, sags, plaster defects, stuff like that. It has to be uniform, and no evidence of lapse or breaks in continuity. This is obviously a bit subjective. I may think something looks really bad, the contractor says, oh, that's perfect. And so we have a lot of arguments that it can't be at that. And so then there's, again, more things that we have, including in our special provisions of page 4 dashes. We're not going to do any more concrete quantities, but there's some things if you want to do some practice, we could have some quantities, some of the, it gets a little things of how you split those up, little triangles and stuff. So, what part of the bridge is the portion that transfers the load from the deck and the beams to the ground? The substructure, very good. What types of abutments can accommodate thermal movements at the roadway and the approach panel? Integral and semi-integral, very good. Keep the height of free fall of concrete to a maximum of what? 4 feet. And why? Segregation. Deposit the concrete as near its final position as possible. I actually didn't talk about this. What can't you use to move concrete from, you put it out here in the vibrators. So a lot of times it's easier for the, especially if you can say a higher abutment and you're putting the elephant trunk down and you're putting concrete here, and now to get over here 5 feet away, you got to lift that all up, put it over, get it between all those rebar and get it back down. So the contractors say, well, why can't I just use my vibrator to pull this stuff over? Well, same thing, it'll segregate. So the vibrators should not be used to move it horizontally. Type 1 concrete, I didn't talk about this one either. It's concrete without what? Air. Without air. So you guys have taken the concrete classes, so you're well aware of that. General, unless otherwise indicated, contractor will be paid for how many inches of excavation on each side of the foot? 6. So 1 foot, 12 inches. What type of construction joints are permitted as a convenience? Permissible. And if it's a mandatory construction joint, what would it be called? Construction joint. There's also, like in railing and sometimes in the smaller abutments, we can also call them contraction joints. But construction joints would be that. This type of finish to be completed on all vertical concrete surfaces. Ordinary is correct. SSF stands for what? Special surface finish. And where do we get the requirements for material testing? Digital materials. Okay, very good. So I have a Mentimeter left. Let's take like a 5-minute break. It's been a long session there. So let's go till 4 o'clock. Good, that's why we're. So it's 5 equal spaces. That line, so between those, there's 5 spaces, so there's 6 cars. 5 spaces, yep. Yep. No, so then, so this bar, so if this bar is going parallel. And then this one would have, like, that's 5.5. No, that's more like 8, because you have 4 is what, 40 inches divided by 5 equals.
Your face,
so 3 foot 4, so 36, 3 foot is 36 inches plus 4 is 40. So you
Yeah.
have 40,
Everybody's doing like
I got nothing.
so the spacing right there is 8.
I had to do the,
From here,
I
from
think I
8
did it.
inches, and that would be where that one sits, 8 more inches over here, 8 more over here, 8 more.
I got nothing. I couldn't understand what he said. Nothing.
Yeah, that's all I did. 3 foot 4 is 40 inches, so you could do, yeah, you could do, 3 times 12 would be 3 feet times 12 inches per foot would be 36.
Yeah.
No, I'm done.
So if you,
Walked out.
what do you design it called?
Yeah, no, like I was horrible. Horrible. I was like,
Oh, you could go down.
No, something.
Yeah. So that would be.
No.
You could take.
What it was, right off the bat.
Divided by 5.
There's a restaurant actually attached to the hotel.
Yeah, so then, like, if you just, so add 3 to that. So you add 3 plus 3. And now you divide the 5 equals.
What do they give you for dinner? Like $40?
Equals, so that's 0.67 feet. And if you multiply it, so on the feet, or if you want inches, now you get 0.67 times 12, and it'll come back to 12. So there's different ways to do it. 8 inches on that side, and on this side, you do the same. But just for ease, you could say 20, I mean, 1 foot 11 is 22 inches. Divided by 5 spaces, and you're almost 5.
Yeah, but you know, $10 cash.
So this, yes. So those are gonna be like 5 inches apart.
Your hotel.
So down here, they're 8 inches apart, and down here,
Corey will give you breakfast? I would say, I would just tell them that you have a gluten allergy and there was nothing gluten free, so I had to go.
Yeah. Jeremy.
Just put it.
But it was $10. He's like, we don't have your receipt, you get it, you can wait 10 minutes.
We have waiting slot for it, depending on what you're getting, I guess, but. Oh, yeah, well, it's, I mean, it depends on where you go, but.
I work with you.
Yeah, because I mean, that's, so it depends on where you go for breakfast. I don't even know if it is. I haven't been to McDonald's for 50 years.
Those for miles.
Hey, when you're expecting one thing and it's not that, you're like, oh.
His mom lives down here.
I know for a while, he was.
Usually, yeah, but I was getting like less than 10 minutes.
He lives in
Oh, nice.